Welcome back to our series on multivariable calculus. In this episode, we're going to talk about the chain rule. In particular, we're going to apply the chain rule to partial differentiation. Suppose we have a multivariable function, f of x and y. But suppose further that x and y are parametrically defined. That is, that x is actually equal to some g of t, and y is actually equal to some h of t. That means a single parameter t can be used to generate values for both x and y, and correspondingly that single value of t would actually generate values for z as well. Well, how would we go about differentiating this function? If I wanted the derivative of f with respect to t, because x and y are explicitly defined in terms of t, I could just make the substitution and do the derivative of f with respect to t. But that's often a lot of work. Sometimes these functions are complex and you'd be better off handling them as separate entities. Well, of course, the chain rule allows us to do this. A quick refresher of what the chain rule would mean for this particular derivative. So if I wanted the derivative of f with respect to t, what I would first need is I would need a partial derivative of f with respect to x. And then I would multiply that by the derivative of x with respect to t. Notice this is not a partial derivative because x is not partially defined in terms of t and some other variable. It is wholly defined in terms of t. So this is a regular derivative, whereas this is a partial derivative because f is actually defined in terms of multiple variables. Well, I would then need to add to this the same term for y. The partial of f with respect to y times the explicit derivative of y with respect to t. And this application of the chain rule, basically taking the derivative of the outer function times the product of the inner function, is something you're very familiar with from single dimension calculus. In multiple dimension calculus, this is infinitely expandable. Had this been a 3-variable function, I would just add on another term. If it went to 4, I'd add on another term. And the same is true for how they were defined here. Each one could be defined in terms of t. Okay, let's take a look at an application of this and show you the advantage of not having to do the substitution before we actually go forward with the differentiation. So the example I'll give you is, suppose we have our function of f of x and y, and just for the sake of argument, it's 3x minus 2y squared. Further, x is defined as 3t, and y is defined as 2t squared minus 1. Well, you can see in order to form the partial derivative up above, as well as the derivatives of x and t, I basically need to differentiate all of these things in order to form the products that I'm ultimately going to multiply. Well, let's go ahead and do that. First, the two partials of the original function. I need fx, and of course that's going to be just 3, a constant. I need fy, and that's going to be negative 4y. And then I need the derivatives of x and y in terms of t. X prime is going to be equal to 3, and y prime is going to be equal to 4t. And now I'm ready to form the derivative of f with respect to t. In essence, the derivative of f with respect to t is just going to be the product of these functions. So I'm going to take first the partial of f with respect to x, that's 3, times the derivative of x with respect to t, that's also 3. And then I'm going to add to that the derivative of f with respect to y, and that partial was negative 4y. And finally, the derivative of y with respect to t, and that was 4t. Now, if I wanted to, I could come back and unsubstitute what y was, 2t squared minus 1, into here, and that way I would have the derivative of f with respect to t explicitly in terms of t. Notice that this is surprisingly easier than making the substitution and then differentiating the original function. Also notice that we can rewrite this in a vector notation, actually exploiting some of the power that linear algebra is going to begin to give us next semester. And that is, If I want to write df dt for this chain rule, one way to do that is to make one vector the two partial derivatives, fx, fy, and then simply dot it with the two derivatives of the parametric functions, x prime, y prime. And you'll notice, what does the dot product do? Well, it multiplies the first terms of the vectors and it adds it to the product of the second terms of the vectors. And so this becomes a really nice shorthand notation for this. It looks cleaner and easier to apply. So you can think of this as the chain rule for any time you want to take the derivative of a multivariable function, which is further defined by a series of parametric equations. It even works if we expand the parameters. That is, we can do another sort of example problem where I've got f of xy, except this time x is actually defined as g, which is a function of s and t. That is, x is defined by two independent parameters. Correspondingly, y is some function of h of s and t. In other words, the parametric equations are themselves multivariable. So we've got a multivariable parent function with multivariable embedded parametric functions. In this case, we have to begin with the idea of a partial derivative. That is, I can't take the derivative of f with respect to t because t is only part of how the interior functions are defined. I'll need it to be a partial derivative of f with respect to t. And of course, what would that look like? Well, following the same model we had over here, what I want is the partial derivative of f with respect to x. And then I want to follow that with the partial derivative of x with respect to t. And actually, because x is defined by the letter g, that's its function, let's go ahead and make it g of t. And this, in essence, would be the first term. And then I would add to this the partial derivative of f with respect to y times the partial derivative of y's definition with respect to t. That would be h sub t. Now, this would only be half of the derivative of f. This is the one with respect to t. I'd have to do it again, df with respect to s, to kind of get a complete picture of the derivative of f with respect to the deeply embedded parametric functions. And this one will look similar. It's fx, and now it'll be gs plus fy and hs. And once again, I could list these in this vector notation over here. So you can see, no matter how complex the original function or its deeply embedded parameters go, the chain rule provides us with some really easy applications of finding derivatives from the explicitly stated functions rather than having to dive too deep within substitution. Our final application of the chain rule is going to involve implicit differentiation. Suppose I had f as a multiple function of x, y, and z, and it equals some constant. But what I really want is the partial derivative of z with respect to x. Well, I could do that if I could isolate z and move everything to the other side, and then I could take the derivative of that other side with respect to x. That would give me dz dx. But suppose z is impossible to isolate. Well, implicit differentiation is exactly designed for that particular situation, the situation where derivatives cannot be explicitly solved for, so you must implicitly locate the derivative, and partial derivatives are perfectly well established for this. Here's how it would work. I would want, say, the derivative of f with respect to x. Again, I choose with respect to x because that's the derivative I want for z. Had I wanted z with respect to y, I'd start off with df dy. Well, I know that's equal to 0 because any derivative of f will be equal to 0 because the f function is actually a constant. But now let's break it down by actually taking the partial derivatives using the chain rule. If I want to take the derivative of f with respect to x, that means the derivative with respect to x of all three of these interior functions. So that means first I need fx times the partial of x with respect to x. It's sort of treating x like it is its own parameter, plus fy times the partial of y with respect to x. Again, treating y as if it's a parameter of x. And finally the same, fz times the partial of z with respect to x. And again, that's my target. That's really ultimately what I'm after. Well, you can see what we can do with this. This is the number 1 because any derivative changes according to its own change by the same rate. And so that's 1. So this is fx times 1. dy dx, that partial is 0 because y isn't a function of x. These are independent variables, so none of them have anything to do with each other. Y with respect to x would be 0. And so the middle term is 0. And then I add on to that the partial of f with respect to z times the partial of z with respect to x. And of course, all that still adds up to 0. So you can see what I can do. I can move the partial with respect to x to the other side. That'll be negative. I can divide by the partial of z, and the partial of z with respect to x will be equal to negative fx over fz. And so that's the answer. If I just take the partials of x and z of the original f, their ratio fx to fz will be the partial of z with respect to x. I could have started out over here with any of the other variables. I could have made this with respect to z, I could have made this with respect to y, and I could find those embedded partials. So that's how you can apply the chain rule in order to take an implicit set of derivatives and still solve for a derivative that could not be explicitly solved for.